everyone, I'm Ziyi, a PhD student at Rice University. I'm very excited to talk about our work Oasis, a system that enables persistent memory oversubscription for emerging applications. Persistent memory, or PMEM, gives us nanosecond-level access to durable data. The CPU can load and store directly into PMEM in just a few hundred of nanoseconds. And this is orders of magnitude faster than accessing data through file systems, either to PMEM or to disk. This fast access opens the door to emerging applications. PMEM-based key-value stores achieve much higher throughput compared to disk-based ones, and crash-resilient libraries can make originally volatile programs crash-resilient by automatically adding checkpoints. And persistent memory data structures provide both crash-resilient and efficiency. They share a similar method of managing persistent memory, and that is to first allocate a PMEM pool up front and map it to CPU virtual address space. It then, during the runtime, do sub-allocations from the pool to utilize their own PMEM pool. This offers flexibility to the application for memory management, but this also creates a limitation in terms of system-wide scalability. When an application starts and the required PMEM pool cannot be satisfied by the remaining available persistent memory, it will run out of memory. And in this case, the number of persistent memory applications that can be run concurrently in the system is limited by PMEM capacity. We observe that although many applications use a large amount of PMEM, they only actively have a small fraction of the memory as working set. The working set can be as little as 9% across a diverse range of PMEM applications. This motivates us to propose Oasis that enables PMEM oversubscription. The core of Oasis is a persistent MMAP. It resembles the original MMAP that maps a disk-based file into DRAM, but it is different from that in the sense that it provides crash consistency. So the application can create a virtual PMEM that provides the illusion of the physical PMEM, and it can directly do load and stores, but the data can be swapped between disk and PMEM. The on-demand page fault will bring the data into PMEM from disk. And when there is more virtual PMEM created than the amount of physical PMEM, Oasis will try to evict the least recently used pages into disk to make room for hotter data and new allocations. In this sense, the system can spawn more applications than non-oversubscribed case. This allows the system to scale beyond the physical PMEM size and achieving higher system-wide performance with more applications concurrently running. The persistent MMAP provides persistency guarantee, and application does not need to change their programming model to use Oasis. Importantly, Oasis deliberately chose to reuse the existing memory management subsystem for managing persistent memory. It inherits a lot of mature memory management advantages that has been evolving for decades. For example, the memory management prefers to create contiguous allocations. Previous study shows that fragmentation kills PMEM performance because allocations that are not aligned to 2 MB boundaries can only be mapped by base pages, which significantly increase the TLB pressure and TLB miss rate. In contrast, with memory management, Oasis supports multi-size transparent huge pages, ranging from 4K, 32K, all the way up to 2 MB. In this case, when 2 MB pages cannot be allocated, it can allocate intermediate-sized pages, and this helps the modern CPU to create 32 KB TLB entries to reduce the TLB pressure. It can also reuse the existing K-huge page daemon that periodically promotes the huge page and defragments. In addition, by managing it as a memory mapped to file in disk, it has got a second chance to do defragmentation during a page fault handling that can coalesce the fragmented file blocks together into a contiguous chunk. As a result, the TLB miss is significantly reduced. Another benefit of reusing mature memory management techniques is that it can utilize the mature eviction policies, such as the 2QLRU policy. The pages are classified as active and inactive. We can reuse the page table entry access bit as access profiling for those PMAP pages and promote the accessed ones to active and move the unaccessed ones to inactive LRU. We evict the tail of LRU. By using this mature policy, we can achieve a significant memory saving with small amount of performance overhead. And we can even plug in more complicated and sophisticated policies such as multi-generation LRU, thanks to the memory management interface. However, as a challenge of reusing memory management system, Oasis needs to achieve crash consistency using the originally volatile data structures, namely the struct page. The struct page contains the important information that maps pages back into a location in the disk. And the flag indicates the page to be free page, clean page, or dirty page. The size of the page indicates the physical size of the page in PMAP. The fields are separated into two cache lines. Achieving the crash consistency using the originally volatile memory management subsystem is challenging due to six challenges. Here, we are going to demonstrate two of them. In the update sequence, CPU performs two updates to the struct page to update a 4K clean page into a 2 MB dirty page. CPU uses log to protect the non-atomic updates, so the readers will only see fully updated or original values. However, this does not work for PMAP. In PMAP, if a crash happens in the middle of the update, it can be left as partially updated, resulting in an incorrect 2 MB clean page. And because the CPU cache can be written back in an undeterministic order, it can also lead to another inconsistency. And this inconsistency will lead to errors during the recovery process and should be avoided. To address this, Oasis decides to surgically augment the struct page update sequence. The first decision it made is to discard all clean and free pages during recovery. In this case, all the partially updated clean pages are discarded, and that minimizes the runtime overhead to crash consistently bookkeeping such pages. This does not affect correctness as they have a replica in disk. It also adds a CL flush before it sets a page as dirty. This ensures that the dirty flag is set as the last step, and before that, all the other information should have been flushed to PMAP. This guarantees that if a page is dirty, the information on the other field of the struct page will be in a consistent state. So as a consequence, we will either get a fully updated page in PMAP or a discarded page. We listed all the possibilities of the different states across CPU and PMAP, and we augmented 4 update sequences in the kernel to achieve crash consistency. We made sure all the dirty page will be left in consistent state after a crash, with only less than 20 lines of code modifications, and this required only 2 additional cache line flushes per update. We implemented Oasis inside Linux kernel within 1,000 lines of code, thanks to the reuse of existing kernel mechanisms. And this is a general approach to other Unix-based kernels. We evaluate Oasis using an emulated PMAP and compare it against a PMAP baseline of XFS PMAP file system. For Oasis, we use a 1 TB SSD for backing storage, and we evaluated a wide range of applications, but we are going to focus on PMAP key value stores in this presentation. Without Oasis, we can only run 3 instances of PMAP key value store before we run out of PMAP. And with that, we can only achieve 4.5 aggregated system-wide application performance. But with Oasis, we can use the persistent MMAP to oversubscribe the persistent memory and run more instances of PMAP applications. In this sense, with 5 instances of PMAP key value stores, we can achieve a 1.8 speedup in terms of the system-wide aggregated application throughput. And we avoid out-of-memory errors even though if we run more instances. The scalability comes from the memory saving capability of persistent MMAP. When the application uses The application originally uses 48 gigabytes of PMEM. With that amount of PMEM, it achieves 3.7 milliamps per second throughput. And with only 10 gigabytes of PMEM, it can also still achieve a 3.4 milliamps per second performance under oversubscription. And this means that it can achieve that is 79% memory usage reduction with a small performance overhead. Without oversubscription, persistent MMAP still offers benefits and limits the performance degradation. For performance gains, it can achieve performance improvements by reusing the existing memory management techniques, such as huge page creation that reduces TLB pressure. And it also moves the expensive block allocation operations out of the allocation critical path, which is covered in detail in the paper. It also introduced low overhead to achieve the crash-consistent bookkeeping, which introduces less than 1% performance overhead. And even though it encounters page fault overhead in the beginning of the application, those page faults are one-time costs and can be amortized by the long-running application. In summary, the persistent MMAP is the key to Oasis. It reuses the existing memory management for PMEM to reutilize those mature memory management policies, such as huge page creation and eviction policy. And we achieve crash consistency inside the originally volatile memory management with low overhead. As a result, we can enable PMEM oversubscription that significantly improves system scalability when multiple applications are running together. It can achieve 1.8x speedup in system-wide performance. We open sourced our code at GitHub, and we are very welcome for future studies. Thank you. We hope Oasis paves the way for better PMEM memory management in the era of CXL.